All right, so today we're going to look at a few different ways of creating trig inverse functions. And we are going to use as our example the function of cosine inverse of x. So to create our inverse trig function, the first thing we need to take a look at is, of course, our original cosine graph, which is here. You guys can see that it's graphed for about a period and a half, and it does not pass the horizontal line test. Any horizontal line that I draw will indeed cross my function at more than one point, which means the inverse, cosine inverse or arc cosine, will not be a function. If we want cosine inverse to be a function, then what we'll have to do is restrict this original cosine graph so that we are able to have it pass the horizontal line test. And what we're going to do is we're going to keep a portion of the graph here that will give us angles for positive ratios, which means we're going to keep a portion near the origin above the theta axis, which is going to be this part right here. And then we also want to keep a portion of our graph for angles generated by negative ratios, which is going to be the continuous part that goes below the theta axis. So the piece here in green that goes from 0 to pi will pass the horizontal line test and will generate our cosine inverse function for us. So here is that restricted piece. The domain of this piece, as you can see, does go from 0 to pi, and the range goes from -1 to +1. Now, the domain and range are going to be very important. It tells us what quadrants we're going to get our angles from and what those ratios can go between. The ratios will never ever, for sine or cosine, be smaller than -1 or larger than +1. So we've already talked a little bit about different ways you can create inverses. One way is to take the ordered pairs, which for our cosine graph, the inputs were the angles theta, the outputs were the ratios of those angles. And just in the first quadrant here are some of the ordered pairs that come from our trig table. An input or an angle of 0 has a ratio of 1. An angle of pi over 6 has a cosine ratio of √3/2. For pi over 4, the cosine ratio is √2/2. These should all look familiar because they're right from your trig table. For an angle of pi over 3, the cosine ratio is 1/2. And for pi over 2, the cosine ratio is 0. Now, for the inverse of this, I'm going to grab a different color here. What's going to happen with all of these ratios? Whoa, I'm having some technical difficulties here. What's going to happen with all of these ratios is that they are going to flip around, or these ordered pairs I should say, and the ratio is going to be the input. The angle that we get is going to be the output. So one way to create the graph is to flip all of the ordered pairs so that the output now becomes the input. And they would, look something like this. And I'm not going to go through all of them because you guys can get the picture here about what's going on. The output becomes the input, the ratio becomes the input, the angle now is going to become the output. So once we swapped all of those outputs and inputs, we could go back to our graph paper and plot all of those swapped ordered pairs. Or another way that we could create an inverse is to see what happens when we reflect all of the points on our restricted cosine graph across the line y equals x. That's where all the inputs and the outputs are the same. Now, when we reflect across this line y equals x, our points do reflect perpendicularly. So this point right here on our graph would reflect across that line y equals x perpendicularly and end up here on the green graph. That's our cosine inverse function. This point right here at pi over 2 and 0 would reflect perpendicularly and projects across, reflects to that point there, and so on. Every point on the red graph, which is our original cosine function, is going to reflect across this line y equals x and end up on the green graph. And the green graph here represents the cosine inverse function. Okay. Now what we need to remember also is that when we reflect the points across the line y equals x, it's also going to swap the domains and ranges. So here is the graph of our cosine inverse function, and notice that it is a function because it passes the vertical line test. And what we've done is now put the ratios on the horizontal axis. The ratios are now our inputs, and we've put the thetas on the vertical axis. So angles are now our outputs. And when we do that, that swaps the domain and range from our original cosine function. Our domain is now -1 to +1, and remember that was the range of our original cosine function. The range then goes from 0 to pi. So what that means is that if we've got a positive ratio that we're finding the cosine inverse of, positive ratio, then any positive ratio here is going to lead me to an angle that is in quadrant 1. However, if I'm finding the cosine inverse of a negative ratio, that is going to lead me to this portion of my cosine inverse graph, and that is going to generate an angle from quadrant 2.